Hi there, this is Mrs. Often with a presentation about function transformations. Our learning targets for this lesson are to be able to transform a function of the form a times f of x minus h plus k using translations, vertical and horizontal stretches and shrinks, and reflections in the x and y axis. You'll also be able to use parent functions to effectively produce transformations of functions and to identify the key features of the resulting function. Some basic parent functions are shown here. Please note there's the constant function, basically a horizontal line, f of x equals c, the identity function, or the general linear function, f of x equals x, the absolute value function, f of x equals the absolute value of x, the standard quadratic function, f of x equals x squared, the square root function, f of x equals the square root of x, the standard cubic function, f of x equals x to the third power, and the cube root function, f of x equals the cube root of x. For most of these functions, the domain is going to be negative infinity to positive infinity, or all real numbers. But for the square root function, because we can only take the square root of a positive number, the domain is from 0 to positive infinity. Please note that you should be familiar with intervals of increase, decrease, or constant behavior, but for the purposes of Math 109, you do not need to know even and odd functions. Let's start with vertical shifts. Vertical shifts move the graph up and down, a translation, and these are added or subtracted outside the function argument. They're generally written as f of x plus or minus k. Now, it's important to know that you may see something written as k plus f of x, or minus k plus f of x. And if you see this, you should recognize this as being a vertical shift, and you should change the order around just to make your life a little bit easier. The picture to the right shows a transformation with vertical shifts. The standard quadratic parent function has been translated up for g of x 2 units, yielding a new range of 2 to infinity with the same domain. And h of x has been translated down 3 units, again yielding a different range, -3 to infinity. Horizontal shifts move the graph left and right. Again, they are a translation of the graph. We add or subtract inside the function argument. It is generally written as f of x plus or minus h. I have only very rarely seen the h written first within the function argument. Here we see an example of a standard quadratic function that has been translated both to the left and to the right. Please note that the g of x function translates to the right, even though it is -3. So you want to be sure that that x minus 3 inside the function argument translates to right 3 units, because we're subtracting 3 from that x coordinate, and so it's resetting at 0. Similarly, when we have f of x plus 2, this is going left 2 units. Whatever x coordinate you have will have 2 added to it. Functions are also reflected in both the x and y axis. The reflection in the x-axis occurs when a is a negative number. This is written as a times f of x with a less than 0. Again, the function is being multiplied by a negative number. This causes the reflection. Here we see a cube root function. -8, -2, 0, 0, and 8, 2 are some key points. And here it has been reflected. This g of x is the negative cube root of x. And as you can see, there is that reflection in the x-axis. The domain and range here have been unchanged. However, if you had something like a quadratic or a square root function or an absolute value, again, that can change the range of the graph. Reflection in y-axis, you'll most frequently see something that's very clearly obvious here with the square root or other functions that are not symmetric about the y-axis. So here I have f of x is the square root of x, and we have h of x is the square root of negative x. Each x coordinate is being replaced with its opposite. We see the negative sign for b of x. The argument of the function is multiplied by a negative number. Function graphs can also be stretched and shrunken, either vertically or horizontally. Vertical stretch and shrink is a multiplication outside the argument of the function, again, the a times f of x. If the absolute value of a is greater than 1, this is a vertical stretch. If the absolute value of a is in between 0 and 1, this shrinks. Obviously, a would not be 0 or 1. If it's 1, we still get nothing going on, no shrink or stretch. If it's 0, we get a pretty boring graph. Here's an example of a cubic function with 3 points identified, and this has been shrunken. F of x is transformed to h of x, 1/2 x cubed. You'll notice that the graph is vertically shrunken. It looks like it's been stretched horizontally, but that's really not happening here. The graph is just being reduced. It is also taking, it may take a longer time to reach the same heights that it does in the original cubic function graph. Horizontal stretch and shrink is easiest to see in some functions like the trigonometric functions, which we'll work with later in the year. But our example here will be a function that is a piecewise function. Multiplication here occurs inside the argument of the function. It's written f of b times x. If b is greater than 1, if the absolute value is greater than 1, this is going to be a horizontal shrinking that will occur. And if b is in between 0 and 1 for the absolute value, it will be a horizontal stretching. Let's look at some examples. And again, a reminder that b less than 0 causes a reflection in the y-axis. So here's my original function, y equals f of x. Initially, we're going to look at a new function, g of x, which is going to be 1/2 as our factor. 2. So g of x is going to be f of 2 times x. So for each of these, I'm taking a value and doubling it and then seeing what it would correspond to on this graph. So my x-coordinate of 1, when it gets doubled, it's 2. And 2 matches with -2 for an output value. So that changes my point -2 to 1, -2. Changes my point from -4,0 to -2,0. The domain of this graph has been reduced from -4 to +4 inclusive to -2 to +2 inclusive. You'll notice that the overall height of the graph has not changed at all. Looking at h of x equaling f of 1/2 times x, that's going to stretch the graph out substantially because I'm taking my x-coordinate and multiplying it by 1/2. So I have 4 multiplies by 1/2 to give 2. Thus, the point 4 as an input value yields an output value of -2. The point 0, 0 remains unchanged, and that's really the only one that, if you're just multiplying within the argument of the function, will remain unchanged. So let's look at putting all these pieces together and graph the function y equals negative 1/2 f of x minus 1 plus 3. We're going to start off with this same function that we had in our last example. You'll notice that it looks like we've got a parabola part here and kind of an absolute value going on. We have a domain going from -4 to +4 and the range going from -2 to +4. So the first thing we're going to work with is what's inside the function argument, x minus 1. We shift the entire graph 1 unit to the right, adding 1 to each x coordinate. Next, we'll move outside and multiply, shrinking vertically by a factor of 1/2. We'll multiply each y coordinate by 1/2. So now we've changed both the domain and the range of this function. Domain is now -3 to +5, and range is -1 to +2. Our next step, which we'll see on the next slide, will involve this negative sign. So our -1/2 x minus 1 will reflect in the x-axis. Here it is here. Once again, a change in the range, -2 to 1 is now what it is. And finally, we're going to shift this up 3 units, changing the range yet again. Our final domain and range are domain -3 to 5, that's inclusive, square brackets on both sides, and from 1 to 4, again inclusive with square brackets on both sides. So I hope you found this little introduction to function transformations and parent functions to be helpful. Have a great day.